And then I know for like, I don't want to go like out the street.
Yeah.
I know, I was.
They're taking it like or so. Yeah, ATF is. What are they doing?
Yeah.
No, I agree. I just want to read this.
Okay.
What will be the last one?
Sorry, I haven't been here this week to do review with you. So I'm gonna push the quiz back to after the break, Wednesday after the break. But I would like to continue with notes. But I'm gonna change the schedule a little bit here. I want to cover this tomorrow. A lot of this is going to be review. This is kind of like putting together the two sine lines from first derivative and second derivative cavity test, and then sketching the graph based off of the slope and the curvature. So I do want to do this, but would like to cover the new content today and then do a little bit of the review tomorrow. So if we can turn to page 26. So this kind of takes a little bit of time to get used to, because we're no longer looking at the original function graph. Well, eventually we're going to get there, where you're not looking at the original function graph, and so your graph is not representing what you hope to represent. So let me start off with something that feels more straightforward, and then we'll talk about, how do we look at an F prime graph and know what the actual graph looks like. So page. Okay. But for now, let's just see if we can create a sine line for this f of x graph. Okay, so a sine line, we're going to create an f prime sine line here. F prime sine line, you're going to be picking out your slope zeros. So tell me where your graph is going to experience slope zeros. Yeah, at 1, where else? Yeah, -3. And I meant for this to be at -1. I know it doesn't quite line up perfectly, but let's just say that it ends up at -1. So -3, -1, and 1, right? Okay, you guys go with that? -3, -1, and 1. Okay, and then on your slope sine line, you're creating your slope behavior, right? So what do you see to the left of -3? What slope do you see to the left of negative? Just in terms of slope. Positive or negative slope? Positive, okay. So positive slope to the left of -3. Between -3 and -1, negative slope, okay. And it just keeps alternating, right? Positive slope, negative slope. All right. Now, let's say we wanted to create a derivative graph for this. Okay, so now let's call this an F prime graph. Now, what's different about the F prime graph is that the y-axis is now defined differently. Before, the y-axis represented your position or your location of your graph. Now, your F prime y-axis, it's not going to represent location anymore. It's going to represent what of the original function? F prime is what? Slope. Yeah, it's going to represent the slope value of your f of x. So the y-axis is now representing the slope value. So it's no longer going to tell us the location is 5 or location is -5. It's not going to say, oh, the slope is 5 and the slope is -5. And to help us map out what we're actually looking at, this is a good reminder. Anything above the x-axis is where my original graph is going to be experiencing a positive slope. Anything below the x-axis is where my original graph is going to be experiencing a negative slope. Anything on the x-axis is where my graph is going to experience a slope 0. So you can imagine that if I'm graphing the slope values of my original graph, it's not going to look anything like my original graph, right? It's going to look very different. But the slope sign line is going to help us act as a bridge between the graph and between f and f prime. So what do you think we can place onto my x-axis? Where are my slope zeros of my f of x function? Yeah, -3, -1, and 1. So they will go onto your x-axis. Okay. Now, we are going to be, we know that our graph has this thread through these points. So that's nice to know that these are kind of anchor points and the graph is just going to be a smooth curve that's going to go through those points. But then where's the graph going to live? So you see how these are all positive slope to the left of -3? We want the graph to live up here. And it's going to look strange because the graph is going to be decreasing in that interval. And that's going to feel strange because it's like, well, my graph is rising. So why is my f prime graph decreasing here? Okay, let me talk about that for a moment. Now, imagine these are slope values. Okay, so let's imagine the slope values of the original function graph. Okay, maybe this is a slope of 3, right? Then what's going to happen as I move closer towards this slope 0 here? Decrease 2, 1, 1/2, 0. You see how the slope value is decreasing? I know these are just ballpark values. These are not exact at all, but you can imagine that the slope is decreasing because the graph is getting less steep. So that decrease of 3, 2, 1, 1/2, 0 is represented here. These are all still positive slopes, but they're becoming less steep as we get towards slope 0. Okay, between -3 and -1, we're experiencing negative slope. Negative slope is going to live below the x-axis, so the graph is going to have to go down and come back up. Some students ask, wait, how far down do I go? Doesn't really matter. This is just a rough sketch. So as long as you know the graph is going to have to go down and loop back up, that's all that really matters. Okay. What is the original graph experiencing in terms of slope between -1 and 1? Positive slope. So positive slope needs to be where? Above the x-axis. So the graph is going to go up and come down. And then finally, to the right of 1, negative slope is going to be where? Below the x-axis. So because we're graphing the slope values instead of location values, our graph will look very different from where we started. Eventually, we're going to have to start here and be able to move our way back up to the original graph using the sign line as a bridge. But right now, I want to start off with something that's familiar and then build out to something that is new. Okay. Now, we can also create an f double prime sign line and create a second derivative graph as well. So from the very beginning of the graph, though, let me highlight a few points here. Let's say that we have points of inflection off the original graph at -1 and at 0. Yeah, I know it's not perfect, but let's just say that points of inflections are at x equals -2 and x equals 0. And the reason why these are points of inflection is because the graph is experiencing concavity that changes, right? So concave down to concave up to concave down. Okay. So let's create a second derivative sign line based off of our original function graph. Points of inflection, we said, is at -2 and 0. Okay, what do you see here? And originally, this graph is experiencing what? Concave down. So indicate that, concave down. From -2 to 0, concave up. And then from 0 on, we have concave down. Okay. So we can also create a second derivative graph. But again, the y-axis is going to change its definition, right? It's no longer representing location. It's no longer representing slope. Now the second derivative is representing what? Concavity of your f of x function. So to help remind us of that, anytime you create a second derivative graph, let's do some labeling here. Above is where my original graph is experiencing concave up. Below the x-axis is where my original graph is experiencing concave down. On the x-axis is where points of inflection is going to live. So guess what we can place onto the x-axis? Yeah, -2 and 0. So -2 and 0. Okay, again, we're just going to thread our graph through these points. And these concave shapes is for the original graph. These concave shapes is not for the second derivative graph. So a lot of times students want to match the shape with the second derivative, but it's going to be a very simple looking graph. It'll be less curves than even f prime. So you're just threading through these points here and locating either whether to start above or below. So where do we want to start? Below. So you're going to start below and you're going to move up to the point because there's a point waiting for you here. And between -2 and 0, where do we want to be? Above. So it's going to have to go up and then what? Come back down. And this sometimes confuses students because they see this is like concave down, but then they see concave up. Again, don't look at the shape here. The concave up, concave down shape is for the original graph. It's not for the second derivative graph. The second derivative graph, you're just trying to pair up the location. That's it. And then finally, to the right of 0, we want the graph to be where? Below again. So your graph would be very simple. You're just trying to make sure that the graph lands either above or below the x-axis, depending on where it needs to be.
Where do we get the 0 from for the?
Oh, right here.
Yes.
Yeah. So I defined at the very beginning. I defined it. I told that this you wouldn't know that points of inflection was at -2 and 0 unless I told you. So I'm telling you that those are the starting points. Now this graph also lines up from an algebraic standpoint. Now, if you look at this here, what degree does this function look like from the function here? The arrows are both pointing down, and there's 3 change in direction here. X to the what? X to the 4th, yeah. But I'll say -x to the 4th because both my arrows are pointing down. Okay. Now, let's just do this from a calculus perspective, right? Let's do power rule. What's the derivative of -x to the 4th? So y prime is equal to -4x cubed. And if you look at this 4x cubed here, x cubed, that lines up with what we expect from x cubed, right? It's a cubic function, right? What's the derivative of -4x cubed? Y double prime is -12x squared. And this lines up what we know from algebra, right? This graph, this parabola, upside down parabola is represented here with my second derivative function. So graphically and numerically, it lines up. So I just want to also draw that connection that what we see here is something that we can also expect if we were to find the derivative from a power rule perspective. Yeah.
Does that, would everybody ever use like a third derivative?
We would only do a third derivative just if it's like a power rule process, but for us, we're not going to deal much with the third derivative. The third derivative would just be something that describes the rate of change of the second derivative, but most of our attention is going to be between the 3 levels: function, first, and second derivative. That's usually it. Yeah. So the difficulty, I think, is going to be trying to get used to starting here and building out your sign line from your f prime and your f double prime sign line. If we can get these 2 sign lines up and running, then everything will become a lot easier. So the challenge is trying to get the sign lines to be built. So let me talk about how that looks, and then we'll do an example where you're starting with f prime. So let's say this is given to you. Okay, if this is given to you, the first thing you want to do is you want to find your x-intercept. Your x-intercepts will be your slope zeros. So -3, -1, and 1. And so that's why they go onto your sign lines. And then you look to see above or below the x-axis. Above is positive slope, below is negative slope. And so above, below, above, below. Okay, so from F prime graph, we should be able to create the F prime sign line. I think the more challenging thing is creating the F double prime sign line. So the way you create the F double prime sign line from your F prime graph is you look for your peaks and valleys. Your max and mins will be the points of inflections of your original graph. So you see how there's a slope 0 where a -2 and at 0. So wherever your slope zeros are, is going to go onto your F double prime sign. And then to determine the concavity, you're not going to look at the concave up, concave down. We don't have that graph in front of us. You're going to look at the slope. If the slope is negative on the F prime graph, that's going to translate to what? Concave down. Because my slope is becoming more negative, that's going to end up looking like a concave down on the original graph. Okay. Whenever my slope is positive on my F prime graph, that's going to indicate concave up. Anytime where my slope is negative on my F prime graph, on my original graph, it's going to look like a concave down graph. Okay. All right, let me see if we can do a couple. So the rest of our practice is just trying to work from here and build the two sign lines and then sketch the graph. All right, so let's go to page 27 and let's look at a few examples. Okay, so top of page 27. Here's the F prime graph. So again, if you're looking at the F prime graph, we have to keep reminding ourselves, this is not the original graph. This is representing the slope values. This is the slope. Your y-axis are the slope values of f of x. So to help us with that, we're going to label accordingly. Above is positive slope. Below is negative slope. And on the x-axis is slope 0.
You gotta work backwards.
That's right. We're not going to work backwards. Yeah. And then, I'm sorry?
We are going to work backwards.
We are going to work backwards. Yeah. So on the AP exam, if they're going to give you a graph, they're most likely going to give you an F prime graph. Okay. And so this is an important skill here to be able to know what that F prime, how to convert that F prime graph to F of X graph. Okay. So I like to use a sign line to kind of use as kind of a bridge between our graphs. So let's create our slope sign line. Okay. First thing is pick off the x-intercepts. What x-intercepts do you see? Right. -4.
-2.
And 1. -4. -2. And 1. Okay. Don't look at the rise and fall of the graph. Look at the location. Where is the graph located to the left of -4? Above or below the x-axis? Below. So below is going to translate to what? Negative slope. So go ahead and put a notation that indicates that the original graph is going to be falling on the. But these are all negative slopes becoming 0. Right? So -3, -2, -1, 0. Still a variation of negative slope, even though it's headed towards 0. It's still a negative slope. Okay, between -4 and -2, what do you see? Positive slope above the x-axis. I know the graph is going up and down, but these are all different variations of positive slopes. These are all living above the x-axis. Between -2 and 1, negative slope below the x-axis. Okay. To the right of 1, still below. Okay. And these arrows are going to be really helpful because our graph is going to have these behaviors. It's going to fall, rise, fall, and fall. Right? So we'll do that in a second. We'll sketch the original function graph in a second. But any questions right now, getting from that F prime sign lines, F prime graph to F prime sign line? Okay, everybody good? Now, let's do this also. Let's also create an F double prime sign line. And this is going to get us the concavity of the original graph. Okay. Now you're going to look at the peaks and valleys, the max and mins of your F prime graph. Okay. Because the max and mins are going to be where your original graph is going to be experiencing the steepest slope, which is going to be where the curvature is going to change, where you're going to get potential points of inflections. Okay. Where are the peaks and valleys of the F prime graph? -3, -1, and where else? One, yeah. So one is it serves two purposes. It's an x-intercept and it's also a peak or valley. So it's going to show up in both sign lines here, but for different reasons. Okay, so -3, -1. I know it's a little bit off here, but I meant for that to be -1 and 1. Okay, so now we can look at the slope. Here, my slope, I know there's a negative slope and positive slope, but they're all moving in the positive direction. So these are all slopes becoming more positive, and therefore that positive slope is going to translate to what on the original graph? Concave what? So yeah, positive slope is going to be concave up. Negative slope is going to be what? Concave down. Positive slope, concave up, and negative slope, concave down. Some people struggle with this because they say, wait, this looks like concave down, and this looks like concave up and concave down. Again, that would be a right interpretation if you're looking at the f of x graph, but this is the f prime graph, so all the rules changes. So we can't look at the curvature and determine the curvature of the original graph. You got to look at the slope to determine the curvature of the original graph. So positive slope on the f prime graph means concave up. Negative slope is concave down. Positive slope, negative slope. Okay. So now we're going to try to sketch the original graph. And I'm going to do this because this is what a lot of students experience. When a lot of students want to sketch the function graph, they end up looking at this graph and they end up copying the exact same graph. But you know it's going to be very different. But it's hard to sketch the graph when you see a graph that's in front of you. So I'm going to cover this up because this is not going to serve us any good now that we have the sign line. We're just, imagine this is the only thing that you see and you're trying to sketch the graph based off of that information. Okay? You're just going to do whatever the arrow is telling you. So what do you expect then for the graph to experience at -4? A relative what? Relative min, okay? What do you expect at -2? Relative max. And then that 1 negative, okay? Now, we don't know where the y values are. So when we sketch our graphs, everyone may have a different min and different max, but everyone should still have the same rise and fall behavior. So I'm going to make my graph more drastic. So if I see a min, I'm going to purposely pick a point lower on the graph. If I see a max, I'm going to purposely pick a point higher on the graph. But your graph may be a different location than mine, but we should still match with the same rise and fall. So at -4, I'm going to just target a point relatively low. Eventually, I want my graph to experience that negative slope. At -2, I want my graph to experience a relative max. So I'm going to highlight a point pretty high on the graph. And then at 1, I know my graph is going to fall, but continue falling. So I'm just going to pick a point somewhere between. So are we good with just looking at the arrows and just trying to sketch our graph? Okay, we'll do 2 versions of this graph because we're going to have to do a curvature version of this graph as well. But doing 2 things at once is a little overwhelming. Let's just do one thing at a time. So I'm going to use dotted lines to kind of map out the path of my graph, but I'm not going to commit to the curvature of the graph. I don't know the curvature yet, but I do know there's relative min at -4. There's relative max at -2, and the graph is going to continue falling, flattening out at -1, but then continue falling. So I'm going to use dotted line here just to kind of map out my path. Decrease until a relative min, increase until it hits a relative max, decrease until it flattens out at 1, because at 1 there is going to be a slope 0. So I'm going to have a leveling off, and the graph is going to continue falling after that. Again, I'm just using the arrows to inform how my graph is going to move. Okay, are we good so far? Okay, we're going to go back and we're going to retrace this graph with curvature information. Okay, now when you do curvature information, you're not going to create a new path. All you're doing is you're retracing it with the proper curvature, but you're not going to create anything that's not already there. Okay, so don't forge a new path from the concavity sign line. Everything is here already. You're just going back and you're just giving it a little bit more detail along the path. So wherever the graph lands at -3, -1, and 1 will be your points of inflection. So we may all have different points, but wherever the graph lands at -3, go ahead and highlight that point. Wherever your graph lands at -1, highlight that point. Wherever your graph lands at 1, highlight that point. So we've highlighted these 3 points, and now we're going to go back and retrace it with the curvature that we want along that path. So initially, we're going to start with concave up. So up until the first red dot, I'm going to give it more complete picture, that concave up shape. And then from -3 to -1, I'm going to give it a concave down shape. I'm going to kind of over exaggerate it. From -1 to 1, back to concave up. Not going to be a full concave up, but it's going to still have that shape along that path. And then for the rest of the graph, concave down. And so again, I'm not creating a new path. I'm just retracing across my dotted line with just a bit more detail from what the concavity sign line tells me. Okay, so we have our f of x graph. Let's also sketch our f double prime graph. So f double prime graph, your x and y axis, your y axis is again redefined. There's no longer position, there's no longer slope, it's now concavity. So let's label what we want on our second derivative graph. Above is concave up, below is concave down. Anything on the x-axis is going to be your point of inflection. So we have our second derivative sign line. What can we place onto our second derivative sign line? What's on the x-axis? Yep, -3, -1, and 1. Okay. And all you're doing is you're just threading between these points. Don't look at the shape. We're not going to match the shape at all. We're just wanting to make sure the graph is either living above or below the x-axis. So where do we want the graph to start? To the left of -3, you want the graph to be where? Above. So if it's above, it's going to have to come down. So if it comes down, it'll just be like that. Okay. Between -3 and -1, where do we want our graph to live? Below. Again, the shape is not going to matter. Okay. It's going to go down and come back up. Some students feel like this is conflicting because they see, well, this is concave down, so why am I doing concave up? Again, the shape doesn't matter. Okay. The concave up, concave down, we've already done that for the f of x graph. The f double prime graph is more about the location. So don't look at the shape, just match the location. Okay. Between -1 and 1, where do we want our graph to live? Above, right? Concave up. So it's going to go up and come back down. And then to the right of 1, low. Now, filling out your characteristics is going to feel easy if you have the sign lines in front of you. So increasing, you're just going to pick out the interval where there's an arrow pointing up. For decreasing, you're just doing intervals where the arrows are pointing down. Relative max, we have one relative max at x equals -2. Relative min, x value of -4. For concave up, concave down point of inflection, you're just pulling your intervals and your points from your second derivative sign line. Okay, so go ahead and try that. All you need is the sign line to fill this out. This should feel easy now that you have your sign lines in front of you. All right, this is all we're going to do today. We're just going to practice getting from f prime to f of x to f double prime. And because you don't know the y values of your max and min and your POI, you're just going to present your x values. Okay, let's look at the next problem down, number 4. Sorry, I mislabeled the letters here. I meant for all this to be G prime, G or G function. Does anybody still need this page? All right, example 4. Our derivative graph is provided. First derivative graph is provided. First thing is go ahead and label what you're looking at. Above is positive slope. Below is negative slope. On the x-axis is slope 0. All right, so what can I place onto my slope sign line? X-intercepts, -2, 1, and 3. Okay. Don't look at the rise and fall, look at the location. Where's my graph located to the left of -2? Yep, above the x-axis. I know it's decreasing. That decreasing will come in later when we talk about concavity. But right now, look at the location. It's above the x-axis, so that's going to correlate with positive slopes. These are just all different variations of positive slopes. Okay. Between -2 and 1, still above. Yeah, still rising. Between 1 and 3, negative, below the x-axis. To the right of 3, positive. So the graph is going to rise, flatten out for a moment, rise again, relative max, and +1, decrease, increase after a relative min, and it's just going to follow this pattern of the arrows. Okay. All right, we'll do that in a second. Let's do the second derivative sign line. And this is now going to be pulling the concavity of the original function off of the G prime graph. So now we're going to look at the what? How do we find points of inflection off of the derivative graph? Yeah, mins and max. Okay, so mins and maxes. So -2, 0, and what? 2. Okay. Now look at the what of the G prime graph to determine concavity. Look at the slope. Right. So here, what do you see here? Negative slope. So negative slope means what on the original graph? Concave down. Yeah. Concave down. Again, the tendency that students have is they want to look at this and say, oh, this is concave up. This is concave down. I mean, that would be true if this is the original graph. But again, this is the derivative graph. So pulling concavity of the original graph is not going to be your shape. It's going to be the slope. So negative slope is concave down. Positive slope would be what? Concave up. Yep. And then it's just going to keep alternating, right? Negative slope back to concave down, and then positive slope concave up. Okay. The most important part of this problem is getting these sign lines. If you can get these sign lines in front of you, everything is going to feel a lot easier. But the hardest part is just building these sign lines. All right, I'm going to do this. I'm going to purposely cover up my graph here, so I'm not using this to sketch my original function graph. This is not going to do me any good if I'm trying to sketch my graph. All I want to do is I just want to rely on these arrows to help me sketch my graph. Again, you're going to feel a little bit, you're not going to feel anchored because it's like, wait, where's this relative max? Where's this relative min? Again, every student may have a different interpretation. It's okay. I'm just looking for the basic rise and fall of the graph to match. Yes.
Wait, so for G double prime,
Yes.
how did we get the like x-axis values?
Oh, you mean critical points.
Yes.
We picked them off from the max and mins of the F prime graph. Yeah, so the wherever the slope is 0 on the G prime graph is where I'm going to be building that G double prime sideline. Okay, so let me see again. We may all have different y values, and it's okay. But I do kind of want to visualize what my graph is doing, and I like to kind of exaggerate my location here. So at 1, I'm experiencing a relative max. So I'm going to just purposely pick a point relatively high on my coordinate plane. And then at 3, I'm expecting a relative min. So I'm going to pick a point relatively low on the x-axis. Sorry, on my coordinate plane. At -2, my graph is going to be flattening out but continue to rise. So I'm going to just pick a point somewhere between. And now I'm going to sketch my graph. Again, I'll do a dotted line because I don't know my curvature yet. But with a dotted line, I can at least map out the path of my graph, and then I can retrace it later with more information. So my graph is going to rise, flatten out at -2, because anytime there's a critical point, that's a slope 0. And it's going to continue rising. Hit a max at 1, wherever that max is. I just picked a point relatively high on my coordinate plane, and then it's going to fall, hit a relative min at 3, and then continue to rise after that. Again, if your graph is everything is above the x-axis, it's fine. If your graph is all below, it's fine. But ultimately, our shape should match. Okay, so you're not going to create a new path after this. This is the path of your graph. Now you're just going to retrace it with more additional information. So at -2, 0, and 2, wherever your graph lands at those points, highlight those points, because those will be your target as to where you want your graph to begin to experience a change in concavity. Okay, so I have 3 points highlighted. Okay. What's my original curvature here? Concave what? Concave down. So I'm just going to kind of go along my path and produce that curvature that I would like along that path. And then from -2 to 0, back to what? Concave up. So it's going to be more of a U shape. And then back to concave down, upside down U shape. And then back to concave up. All right, let's create our second derivative graph. Second derivative graph, label accordingly. Your y-axis now represents the concavity value of the original graph. So above means concave up, below means concave down. On the x-axis is your point of inflection. So go ahead and place your -2, 0, and 2 onto your x-intercept. And your graph will just be a nice, simple parabola, or a nice, simple polynomial that's just going to thread between those points. Okay, it'll be less changing, less curves and less change in direction from the previous function. This should be the simplest looking one of the 3 because it's the lowest level in terms of the slope behavior. All right, so where do we want our graph to start? Below, and it's going to link up to this point here. So it's going to start below, and we're just threading back and forth between those points. It's going to land above. So come up, back down, below, go down, back up, and then to the right of it to up. So I know we still have to get past the quiz, but after we get past the quiz, after the break, we're going to just add these elements. With this will be, you'll see an extended problem like this, where you're going to be given a derivative graph. You're asked to sketch the function graph. You're asked to sketch the double derivative graph, and then you're asked to fill out characteristics. So there will be an extended problem that's just basically this exact format. Okay, go ahead and fill out your characteristics. These should feel easier now that you have your sign lines in front of you. Okay, next 10 minutes, can we try one on our own just to see where we are? And if we get stuck, it's okay, but I just want to kind of walk around and see how we feel. So if you can turn to page 29, and it's the exact same process. You're starting with a first derivative graph. Create a slope sign line, create a second derivative sign line, and then after that, you're going to start sketching your graphs. So this is page 29. Okay. I'll leave the previous page up so that you can see the steps. So page 29. The hardest part is building these sign lines. If you get these two sign lines, then you've achieved the most, you're basically more than halfway there. And that way, that will also give you a chance to ask questions now that you're trying it on your own. Pull your x-intercepts. Those will be where your slope zeros on the original graph. And then look for location. Above is positive slope, below is negative slope. Second derivative sign line, now you're looking for the max and mins, the peaks and valleys. So here, -2 and 1. Okay, don't look at the curvature here. This is not the original graph, this is the F prime graph. So we want to look at the what to determine concavity. Look at the what. This is what? Negative slope. So therefore concave down. Positive slope means concave up. Negative slope means concave down. Okay, your function graph. Again, it helps if you can visually just like cover up your f prime graph so that it's not getting in the way of distracting you when you're sketching the function graph. We want a relative max at -4 because I'm just looking at the arrows here. I'm expecting a rise, fall, rise, fall. So -4, I'm just going to highlight a point above. -1, I'll highlight a point below. And at 2, I'll highlight a point above. And if you're asking, wait, which one is going to be higher? Is that be a higher relative max, or it doesn't really matter, right? As long as your rise and fall of your arrows matches, that's all that matters. So I have rise, relative max, fall to relative min, rise to relative max, and fall after that. I'm not committing to the full graph. I'm just doing dotted lines because I'm going to go back and give it more detail. So -2 and 1, wherever the graph lands. Highlight those points. And now you can match the curvature of the graph. Okay, concave down, back to concave up, back to concave down. Okay, second derivative graph. Okay, now you're just pulling this off of your second derivative sine line. Okay. Above the x-axis, concave up. Below the x-axis, concave down. On the x-axis, point of inflection. And between the three graphs, this will be the simplest looking one. This will be the one that has the least number of curves. But a lot of students want to over-exaggerate it because they get a lot of students feel like they have to involve these curvatures, and they start making the graphs a lot more complicated looking than the others. So the graph will just simply extend between the points, and it's going to have a lot less curves than the others. Okay? Even though I know these curves are kind of throwing you off. Okay? Where do we want our graph to start? Below. Then it's going to be above, and it's going to be below after that. So it's going to be a very simple looking graph. The shape is not going to be what we care about. It's the location. All you care about from this is it above or below the x-axis? All right, fill out the characteristics. Hey, no homework tonight. Tomorrow, we'll do kind of backtrack and do a little bit of review. Even though curve sketching is a new section, it is still review. And then Monday, when we get back from break, we'll have another day to review, and then your quiz will be Wednesday. Okay. Wednesday after break.
So
Wednesday after.
we on the Tuesday after break, will we review the quiz?
I probably need to do the last section, optimization, but we can still have some time to review in class. And I'll still have a morning review for you the Wednesday, the morning of the quiz.
Yeah.
Yeah.
Thanks, guys. Have a great day. See you tomorrow.
Thank you.
Thank you. Have a good day.
Thank
Thank you.
Thank you for calling.
Thanks, guys.